Welcome to Probability and Statistics. In this lecture video, we're going to talk about what is so-called the scatterplot and something called the correlations. Okay, so here is what's going on. The word linear correlation coefficient. I'm going to start with this this word. Linear correlation coefficient is what we measure the strength and the direction of a linear relation between your x and the y variable. What I'm saying is, back in lecture video for chapter 3, we entering data on the L1 and L2, and I mentioned that L1 is your x variable, L2 can be your y variables. So the word linear correlation coefficient measures the strength and the directions, okay, of the linear relationship between the two variables. So the notation that we're gonna see for the linear correlation coefficient is gonna be abbreviated as R. All right. So here are some of the properties. Okay, and this is not a new concept for many of you, because as you go through algebra courses, you learn about how to draw a straight line of a linear equation or linear function. Okay, so the R is referring to the linear relationship between the two variables. Okay, so the properties of this R, linear correlation coefficient, R is always going to be between -1 to 1. Okay, if R is equal to exactly +1, it means a perfect positive linear relation between the x and y. So just like you can find 2 points on a line and then you can connect them with the line. So if the line go through every single point, okay, for our cases, if a line go through every single data point, okay, that's where we have 100%. The 1 means 100% linear correlation coefficient. Okay, because the straight line goes through every single data entry. All right, -1 just means we have a negative linear relationship. Negative linear relationship simply referring to my straight line have a negative slope. Okay, +1 means perfect positive linear relationship or positive slope, where my straight line will go through every single data entry. All right, now if the R is closer to 1, it means a strong linear relation. So 1 means 100%. If R is closer to 0, it means little or no linear relationship. So that means our data entry could be other types of relation. So on your handout, I have these 8 pictures, okay, showing you a positive perfect linear relation where you can draw a straight line that will go through every single point. Okay, this is a strong positive linear relation. Okay, so these data entries, okay, look like a straight line. Okay, moderate, this one is negative perfect linear relationship. Okay, because it's negative because my line will going down the hill. Okay, this is a strong negative, this is moderate negative, this is no linear correlation. Okay, and these pictures is what we call the scatter plot. Okay, these pictures are called the scatter plot. So so these points are data entries. Okay, so if a data entry appear to be linear, that means I have a strong linear relation. All right, so I'm going to show you how to find something called the regression. Okay, we will do the correlation coefficient R, and I will show you how to do scatter plots. Regression is referring to the line, okay, that will be best fit through the data. Okay, I will introduce that word in the next section, officially introducing the next section. All right, so we're going to go by the step Choosing edit, we're going to enter our X and Y values under L1, L2. Alright, we're going to press Stat, Calc, and choose this thing called the linear regression. Okay, so that's how we're going to get a regression. So I will show you on these steps just in a minute. Okay, so let's try an example first. Okay, let's try an example first. Alright, the following data, okay, give the number of hours 10 students spend studying for their corresponding grades. Okay, so hours spent studying. Okay, got half an hour, 1 hour, so on. And these are the midterm grade. Okay, draw a scatter plot for the given data. So I will show you how to draw this on the calculator real quick. All right, show you how to draw this on the calculator real quick, and then when I go over the project, okay, I will show you how to draw it by hand. All right, so if I go to my calculator, press Stat, Edit, okay, go ahead and type in. So the hours spent studying is going to be my X variable. Okay, my output or my Y variable is going to be the midterm grade. So let's type in these. $6.99. Alright, so once I key it in, we'll press Stat, highlight the word Calc, choosing number 4, linear regression. Okay. Alright, I'm gonna go ahead and press Enter for linear regression. Okay, I'll show you what these mean just in the next lecture video. But right now, what the problem one is draw the scatter plot for the given data. So to draw a scatter plot, let's go back to the previous page. Okay, just to draw the scatter plot, okay, I need to turn on my scatter plot, press zoom, and choose zoom stat. So for my problem, I'm gonna go to second stat plot, number 1. Make sure I turn on my plot 1, press enter. Then I'm gonna come down, choose the first one. The first one is actually your scatter plot. Alright, my X and Y list is on the L1, L2. Alright, press zoom, and number 9 is called zoom stat. It automatically fixed the window for you, just like when we did the histogram. Alright, so here we go. So this is your scatter plot. So does this scatter plot appear to be linear? So let me kind of copy this real quick. So this is my scatter plot. Oops. Alright. Estimate a correlation in words. So this look like a linear correlation. Okay, it look like, you know, they almost form a straight line. So is this a positive, negative, or there's no correlation? So the answer got to be positive, because this thing is going upward from left to right will be positive linear correlation. So how do I calculate the correlation coefficient R? We can actually calculate the correlation coefficient R from the calculator. So let me go back back to this home screen. So when we did the linear regression earlier, okay, there should be more things being displayed. So do me a big favor. To find this correlation coefficient R, I need you to go press second in the word catalog, which is number 0. Alright, right now you got the letter alpha right here. So press the letter D, which is right beside the matrix, or X inverse. So when I press X inverse for my letter D, go down and look for something called diagnostic on. Diagnostic on. Press enter. Press enter. Alright, so once it says done, let's go back and do my linear regression again. So back to stat, highlight the word calc. Alright, number 4, linear regression. So now we just got to do this. So now when I turn on the diagnostic, every time when I do linear regression, it will display what I wanted. So the linear correlation coefficient R, alright, is this number right here, 0.982. My R is equal to 0.982. So that means, okay, that means the strength of the strength between the X and Y variable is about 98.2% strong. So this thing is basically, okay, has a very, very strong relation. Okay, the closer to 1, the better. All right. As far as collecting data and then draw a scatter plot, if the R is equal to exactly 1, there should be something wrong with the data. Okay, that's just my personal opinion, because as we collect data, it shouldn't, it shouldn't be exactly like a straight line, okay, in statistic. But the closer to 1, the closer to 1 means closer to being 100% linear relation, the better it is. All right, let's try another one. Okay, just in a minute. All right, so let me show you what this R squared is. Excuse me. Excuse me. This R squared, okay, is actually called coefficient of determination. All right. Now, before we do that, real quick, using what we so-called the critical value of the Pearson correlation coefficient to determine the significance of a linear relation. So what it's saying is, okay, let's say I have a simple correlation coefficient R. Is it statistically significant? If the R is statistically significant, that means my absolute value of my linear correlation got to be greater than or equal to this thing called R sub alpha, or the Pearson correlation coefficient. Okay. So what it's saying is my R statistically significant? Okay. If it is, this R got to be bigger than or equal to, all right, what is so-called the Pearson correlation coefficient. So determine whether a given correlation coefficient is statistically significant at a specific level of significance in a sample size. So let's say I have a linear correlation coefficient R that is a negative. Negative means scatter plot going downward. It's 0.627. So that means my linear correlation coefficient, my strength between the X and Y variable, is only about 63%. Okay, not very strong at all. But is it still statistically significant? So my alpha is set at 0.01, okay, at a sample size 29. So for us to determine whether this simple R, okay, the simple correlation coefficient, whether it is statistically significant or not, we do an absolute value of my simple correlation coefficient, negative 0.627. Okay, it got to be greater than equal to this R sub alpha, Pearson correlation coefficient. If it's greater than, then it is statistically significant. So anything coming on the absolute value is positive, right? So that's 0.627. So how do I find this R sub alpha? We need to go to your formula sheet on the very last page of a formula sheet. Okay, it's called the critical value of the Pearson correlation coefficient. So if you look on this last page of a formula sheet, All right, my alpha was set at 0.01. Go down to sample size 29. Okay, it's 0.471. So if my sample R is bigger than equal to the critical value of the Pearson correlation coefficient, then we are statistically significant. Okay, even though I don't have a very strong linear relation between the X and Y variable, but the data is still statistically significant. Okay, that's what this problem is trying to tell us. That's what the table is there for. Alright, so earlier you saw the R squared. R squared is called the coefficient of determination. It's a measure of proportion of the variation in the response variable Y that can be associated with the variation in the explanatory variable X. So those are the words that we learned from lecture video in chapter 1. Okay, so coefficient of determination. Okay, it measures the percentage of the variation in the response variable, okay, that can be associated with the variation in the explanatory variable X. So for example, okay, the data in the table is a number of absence for 5 students doing their corresponding grades. Okay, calculate the coefficient of determination R squared. So all you need to do is type in these data. Okay, so our explanatory variable is X, or our independent variable is X. The response variable or dependent variable is your grades. Alright, so let's type it in. Stat, edit. Let's clear out what I already done. Alright, so number of absence 5, 8, 9, 10, 11. 5 absence, 90 is the grades. 8 absence, 78. 74 for 9. 62 for 10 absence. 58 for 11 absence. Okay, once we enter in, press stat, calc, choose number 4, linear regression. Alright, so my R squared, okay, 0.950, or we can do, yeah, 0.950, round to 3 decimal places. Okay, our R, the problem doesn't ask for R. Our R is negative 0.974. So negative means this scatter plot will going downward from left to right. It's almost 97%. It's a little bit over 97% strength between the X and Y variable. Okay, correlate coefficient of determination. All right, so this is a very strong variation. Okay, this is actually a good number. 95% is a good number. We don't want these R or R squared to be, to go outside of 90%. So if I will actually go to zoom, press number 9, zoom step. Here are my 5 datas. Okay, going downward. Almost a straight line. Okay, close enough. So what is this line I keep on talking about? The line I'm keep on talking about here is called linear regression. Okay, the least square regression line, or the linear regression, is referring to a linear line that will minimize the sum of the square errors or residuals. Okay, in other words, this line, okay, there's going to be a line go through here. Okay, it will be the best line that will fit the data. Okay, it's called the goodness of fit. So my data appear to be linear. Okay, so I can draw this line, and this line is going to be the best fit. Okay, that will actually fit fits the data. It's not going to connect every single dot, okay, but it's the best fit to my data, okay. And that straight line will minimize what is so-called the sum of the square errors, or residuals. So a residual is the difference observed by the y. It's a difference of observed y and the predicted y. All right. So what that means is the predicted y, okay, will be the linear regression. Okay. These data value is what we already observed and collected. All right. So the point here is, what we're trying to do here is learn how to draw a regression over a linear line that will best fit through the data that we collect. So do you remember something called y equal to mx plus b? Okay. So here we're going to see different notations. Okay. M is your slope. Okay. So the first one, the b1 is your slope, m is your slope, m is your slope, a is your slope. This form will be b is your slope. Okay. So, and you can probably call the y equal to mx plus b the linear function, the standard form for the linear function. Okay. So we don't call it the y when we're here, we call it the y hat in some forms. All right. So let me show you how to draw this. Okay. Prediction should not be made with a regression model if the data do not fall in a linear pattern. Okay, correlation coefficient is not statistically significant. Okay, we shouldn't make any predictions. You wish to make a prediction about a value outside the range of the sample data. The population is different than from which the sample data are drawn. So the purpose of drawing a linear regression is to make predictions. For example, if we go back to this problem, okay, and say, well, I wonder what happened with 7 absence. 7 absence is what grade would they get based on this, okay, based on the data we collected. Okay, so if I will come out back to my home screen here, okay, linear regression, y equal to x plus b. Okay, a is your slope, so my slope is negative 5.43 something. My y-intercept, which is the b, is at 119. So once I got my linear model or linear equation, now we can make our predictions. Okay, that's the purpose, okay, that we're trying to draw this linear regression. So to draw the linear regression, if we go back to the beginning of 12.1, all these steps right here, draw the linear regression, what you gotta do is press y equal, make sure these things are cleared out, press the word vars, choose number 5, statistics, highlight the word EQ, and choose number 1, regression equation. So what that does is it is copy and paste the entire slope and y-intercept, okay, into your y1. So now when I press graph, since I already did the zoom stat earlier, now when I press graph, this is the best line that will fit through this model or fits through this data. So earlier I mentioned the word called residual. Residual is the difference between the observed data, my points that I plotted, versus the predicted value, the point that's on the line. Okay, so this line minimizes, okay, your residual. That's why this line is the best fit for my data, okay, that I collected. All right, so let's try an actual example here. All right. The table below gives the number of hours spent unsupervised each day, as well as the overall grade average for 7 randomly selected middle school students. So use this data, consider the equation of the regression line, okay, in this form, y equal to mx plus b, for predicting the overall grade average for middle school students based on the number of hours students spent unsupervised each day. Okay. Keep in mind, the correlation coefficient may or may not be statistically significant for the data given. So remember, in practice, it would not be appropriate to use regression line to make a prediction if the correlation coefficient is not statistically significant. All right, so let me do this real quick. I'm going to go back out. My linear regression says y equal to ax plus b. All right. So my a is the slope, okay? The b is the y-intercept. So this form, the y-hat form, okay, b sub null plus b sub 1x. So b sub 1x, okay, got to be my slope. So in my form, b sub 1x, the b sub 1 is my a, the b sub null got to be my y-intercept, okay? So one form is what's written in the textbook, the other form is what shows up on the calculator. Okay, a is b sub 1, b is b sub null. Alright, so find the estimated slope, which is finding a, which will become my b sub 1. So let's key this in so we can actually find the slope. And when my a is negative, that's a negative linear correlation. Okay, positive a means positive linear correlation from left to right. Let's key this in. 0.5, 1, 1.5, 2.5, 3, 4.55. So 94, 87, 79, 74, 72, 69. Uh-oh, messed up. Yeah, messed up. Alrighty. So find the estimate slope. So I gotta do a linear regression. So once you key it in, press stat, highlight the word calc, choose number 1, one variable statistics. Alright. I already turn on my diagnostic, so my R will show up. Okay. Oh Lord. Press the wrong button. Calc, choose number 4, linear regression. Excuse me. So I'm gonna just kind of copy and paste this real quick. Alright, so here is what show up. Okay, so my estimated slope run to 3 decimal place. My estimated slope in my form will be b sub 1. So my b sub 1 or my a is negative 0.081. Excuse me, negative 5.081. Alright, my estimated y-intercept is my b. Okay, 3 decimal place, that will be 93.065. So that's my b sub null or the y-intercept. Determine if the statement all points predicted by the linear model falls on the same line. Is true or not true? That's kind of a strange question. So why don't we draw the scatter plot? All points predicted by the linear model is going to fall on the same line. That's the key word, predicted. So what it's saying is, if I want to do any prediction, maybe like 2 hours on supervised, what's the grade? For me to come up with that, overall grade, it got to be predicted value. So of course all the predicted value got to be on the line, because that's the line I'm going to draw. So why don't I just draw this line right here? So I'm gonna go back to y equals, clear out whatever I had done earlier. Alright, to copy and paste all the entire linear regression, I go to vars, number 5. Go to EQ, number 1. Alright. Press zoom, number 9, and you'll draw the line. So this line is the best line that will fit through my data. So is all the point that I'm going to predict falls on the same line? Of course, because I'm using this line to predict whatever I want to predict. So I wonder, 2 hours of being unsupervised, what's the grade gonna be? So I go to second table and just look up under x equal to 2. 2 hours unsupervised, grade is about 82.9. So this point got to be on what? On this line. Okay, so the answer is got to be true. All the predicted points by the linear model got to be on the linear model line. Alright, find the value of the coefficient of determination. So that's looking for the r squared. So I'm gonna do second quick, r squared, 3 decimal places, 0.929. Alright, our linear correlation coefficient is negative 0.964, which is a very strong linear correlation. Okay, it's almost 100%. So that line is the best line that will fit through my model. Alrighty. Alright, let's try another one. Table below give the list price and the number of bids received for 5 randomly selected items sold through online auctions. Okay, so we're gonna come up with this regression line, okay, to predict the number of bids. Oh, by the way, what is my regression? What is my model? My model got to be y. I'm going to type it. My actual model is going to be y equals, okay, my slope, what is use 3 decimal places, negative 5.081 plus 93.065. So that's what my model will look like. Okay, so if you put the beta 1, beta 0 together, oh, forgot the x right there. This is what my linear model is, okay, that I use to predict, okay, anything I want to find out. So I got price in dollar for this example. I got number of bids. So it appears that the higher the price dollar, the number of bids goes up. Okay, so that's your linear relation right there. Find the estimated slope. So why don't we key this in? Stats, edit. I'm gonna clear out my L1, L2. Alright, $23, $26, $28, $34, $49. 1, 2, 5, 9, and 10. Alright. Once I key it in, stats, calc, choose number 4, linear regression. Here we go. My estimated slope is my A, 0.345. My beta 1. Right, my estimated y-intercept, which is my B or beta 0, negative 5.642. Is it right? Beta 0, yeah, negative 5. Here, 5.642. Alright. Determine if the statement not all points. Oh Lord. Not all the point predicted by the linear model falls on the same line. Is that true or not true? It's gotta be false now. All the predicted value got to fall on the same line. So it says not all points. So that's false. Alright, determine the dependent variable y hat at x equal to 0. Okay, so your y hat is your y. So let me do it right here. Okay, so what is my model saying? My model got to be y equal, or according to the model written in the book, y hat got to equal to negative 5.642, right, plus 0.345x, because the model written in the textbook is y hat equal to b sub null plus b sub 1 sub x. Right? So the A, once again, the A is b sub 1. The B from the calculator is b sub null. So when x equal to 0, when this x equal to 0, 0 times 0.345 is 0. So at the beginning of time of this model, or x equal to 0, okay, your dependent variable is going to be the same as your y-intercept. So that will be b sub null. Okay. Alright. Find the value of coefficient of determination. So that's a r squared. Oh, sorry. R squared, 0.778. Okay, R is equal to 0.778. So just for extra measure, I'm gonna go ahead and do my regression real quick of the y equal. I'm gonna clear. Is this the same problem? No, I'm gonna clear this out. Go to vars, number 5 statistics, EQ. Do my regression line. And I'm gonna press zoom, number 9. So there you go. Alright, so this is my scatter plot and my regression line in the same picture. Okay. Alright, remember my R was only 0.88, so it's actually 88% fit. Okay, so you can see the difference. Okay, I got this data value is way off from my regression line. Let's go back to 12.1 real quick. Remember the critical value of Pearson correlation coefficient. So my R, the R I just came out with, is that greater than or equal to R sub alpha. Okay, so let's just do another example. Is my R, is my 0.778 greater than or equal to, okay, my R sub alpha? So if I say alpha is set, the level of significance is set at 0.01. So this got a lot to do with okay, with the things we talk about. Okay, what's outside. Alpha is area to the right for 2 tails. Okay, alpha is just only 0.1 if it's a 1 tail test. Okay, so you'll relate back to that, but I'm not gonna go back and talk about much about those again. I'm just, what I really want to show y'all in this lecture video is show y'all how to find the correlation coefficient R and find the regression, and of course drawing the scatter plot. So if I just set alpha to be 0.01 and I have how many sample size? 5 students. If I go look up in the table, 0.01, 5 students, 0.834, excuse me, 5 students, 0.959. 0.959. So what it's telling us is my R is not greater than the R sub alpha. So I should not make any prediction. Okay, so my correlation coefficient is actually not statistically significant. So we should not use this data to make any predictions. Okay, because the sample size is really not that big. Okay, so that has a lot of factor. That's one of the reasons why the data is not that good. Okay, You want at least 30, right? Remember, talking about sample size to be at least 30 to be normally distributed. Okay. Now, if I will set my alpha to be 0.05, the area, okay, outside the normal curve to be 0.05, okay, then that would be 0.878. 0.878 is still going to be what? My R is still not going to be bigger than the 0.878. So, can't use this particular model to do any prediction. Okay. Alright, so that will conclude our lecture video on how to find linear correlation coefficient R. Okay. We also found we also use a critical value to determine whether our sample correlation coefficient R is statistically significant in the coefficient of determination. We also talk about our linear regression, how to draw the scatter plot as well. Alright, thank you for watching.